Momentum. What even is it and how does it work? Momentum is defined as the quantity of motion that an object has. This is equal to the mass of the object multiplied by its velocity. As velocity is a vector and it's being multiplied by mass, which is a scalar quantity, momentum is a vector, meaning it has both magnitude and direction.
The conservation of momentum states that the total momentum before a collision is equal to the total momentum after a collision, given that it occurs within a closed system, meaning there's no external forces acting on the objects.
There are two main types of collisions that occur between objects, these being elastic and inelastic collisions.
In an elastic collision, the total momentum before the collision is equal to the total momentum after the collision. On top of this, the total kinetic energy before the collision is also equal to the total kinetic energy after the collision, meaning that the total energy is also conserved. This is because during the collision all energy transfers occur within the kinetic energy stores. This makes elastic collisions rare in day-to-day life as there is almost always some energy transferred to other forms.
In an inelastic collision, the total momentum before the collision is equal to the total momentum after the collision. However, the total kinetic energy before is more than the total kinetic energy after. This is because during the collision, energy has been transferred to other forms such as sound and heat, and some work may have been done to deform the object during the collision.
Here is our first example, which is a collision between two carts on an air track. Both carts have a mass of 0.1 kilograms, the moving cart has a speed of 0.5 meters per second. Calculating the momentum before the collision gives us P equals mv. P equals 0.1 times 0.5 equals 0.05 kilogram meters per second. Calculating the kinetic energy before gives us Ke equals 0.5 mv squared equals 0.5 times 0.1 times 0.5 squared equals 0.0125 joules. As the moving cart collides with the stationary cart, the moving cart stops and the previously stationary cart moves off with a speed of 0.5 meters per second. Now, the total momentum after P equals mv, P equals 0.1 times 0.5 equals 0.05 kilogram meters per second. The total kinetic energy after is Ke equals 0.5 mv squared equals 0.5 times 0.1 times 0.5 squared equals 0.0125 joules. Here we can see that the total momentum and kinetic energy is conserved, showing us that the collision is in fact elastic. Here are two muscle cars, both of mass 1,800 kilograms, which will crash into each other with an equal speed of 60 miles per hour.
Firstly, we need to convert 60 miles an hour into meters per second. To do this, we can firstly put it into kilometers per hour by multiplying 60 by 1.6, giving us 96.6 kilometers per hour. We then multiply this by 1000 and divide it by 3600 to get 26.8 meters per second. To work out the total momentum before, we do P equals m1v1 plus m2v2. So substituting the values in, we get P equals 1800 times 26.8 plus 1800 times minus 26.8, giving us 0.
The total kinetic energy before equals 0.5 m1v1 squared plus 0.5 m2v2 squared. After the collision, both vehicles immediately stop moving, so they have a velocity of 0 meters per second. This means that the momentum after the collision is 0, which is the same as the momentum before the collision, showing us that momentum has been conserved. The total kinetic energy after the collision is 0, which is lower than the total kinetic energy before, meaning that the collision is inelastic. Energy has been transferred in the form of sound and heat, and work has been done to deform the cars.
So, our crash participants today is this red van of mass 2800 kilos and this white muscle car, mass 1800 kilos. This red van will be going into this white car at 40 miles an hour. Now let's see what happens during this collision. The coalesced. Firstly, we need to convert 40 miles an hour into meters per second, giving us 17.9 meters per second. Now we can work out the total momentum before using P equals mv, which gives us a value of 50,120 kilogram meters per second. The total kinetic energy before the collision is equal to a half mv squared, which gives us 450,000 joules. From looking at the video, after the collision, the cars coalesce, which means to form one mass. So the momentum after P equals m1 plus m2 multiplied by v. Given that the momentum before is 50,120 and that momentum is conserved during a collision, m1 plus m2 times v gives us 50,120, leading for the value of the velocity to be 10.9 meters per second. Converting this value back into miles per hour gives us 24.4 miles per hour, which is identical to the maximum speed recorded by the stationary car immediately after the collision. Looking at the kinetic energy after the collision, 1,000 joules. As we can see, the kinetic energy after the collision is a lot less than the kinetic energy before the collision, showing us that the collision is inelastic.
Now let's have a look at what impulse means and why this concept is important for passenger safety. Impulse is the change of momentum of an object when the object is acted upon by a force for an interval of time. Impulse can be calculated by multiplying the force by the time or calculating the change in momentum.
Going back to example 2, the car has decreased in velocity from 26.8 meters per second to 0 meters per second. The collision lasted for 0.12 seconds. We can work out the change in momentum of the car to be impulse equals m times delta v, which is 1800 times minus 26.8, giving us minus 48,240 kilogram meters per second. We can now work out the force acting on the car. Minus 48,240 equals 0.12 times F. So the force must be minus 402,000 newtons.
For a passenger, this force will be fatal, which is why safety measures are in place to increase the time and momentum change, reducing the force on the passenger. Seatbelts stretch under high loads, and airbags inflate, which both increase the time taken for the momentum of the passenger to change, potentially saving their life.
Epic explosion!